like William Herschel. I think he said there was deep scaling.
Is it Herschel or Herschel?
Herschel.
You said Herschel then?
I don't think it's Herschel now. Depends where you come from. Germany or
There you go, Herschel then. Herschel.
Found a black hole there, you already.
Sorry?
It's a different
Let's not get
culture.
that's just a bit loose. Right. Okay, right. Tonight I'm going to talk about measuring the universe. You can leave that light on, Graham, it's okay. It helps the camera at the back as well. So yes, we're going to talk about measuring the universe. Right. So this is the way I've structured the talk. I gave this talk to the Society about 10 years ago with some very rudimentary slides.
It's lasted well.
I've revamped it considerably and added in a bit of new information, so it does make it essentially quite a different talk, in case you remember that far back when I did it.
It's a bit bigger though, now, isn't it?
Yeah. It's a bit bigger now.
It's a bit bigger now.
It's, yeah, that's the expanding space, really, yeah.
Is it the steady state of expanding?
Yes. So, this is the structure of the talk tonight. We'll be having a very quick look at the history of attempts to measure the universe. I don't like to dwell too much on history, but you need to know a little bit of what's going on before you know what you know now. Then we're going to look at what tools we need to measure the universe. Then we're going to look at methods using those tools of measuring the universe and go through some practical examples of that. So, quick history lesson anyway. We start off back in 200 odd BC. A chap called Eratosthenes. He was basically the first person to make a documented attempt at measuring the universe. He also, well, not the universe, but more the solar system, because that's all they knew about then. So he measured the Earth, the solar system, and the distance to the sun, things like that. Other notable names are Captain Cook, who was instrumental in determining the value of this astronomical unit, although it's perhaps possible that Charles Green was more the hero of the hour, but he never seems to get a mention. And another notable name is Edwin Hubble, who I'm sure everybody heard of more because of the telescope in his name than possibly of Hubble himself. He was quite instrumental in measuring galaxies and the outer reaches of the universe. So there are some famous or notable names in history in the quest to determine the size of the universe. So, tools. What do we need? You can't get simpler than this. A ruler or a tape measure, or more accurately, a very long ruler or a very long tape measure. Obviously, a ruler or a tape measure to measure the actual universe would be impractical, but that's not to say that we don't need them. We need them to measure a short distance from which we can measure larger distances and so on. So fundamentally, it always comes back to measuring something with a ruler first off to be able to measure everything else. So we still do need a ruler. We need something that can measure angles. Here we have a sextant. There's a graded scale on here, so you can point at something and you can measure the angle that something is above the horizon or from the vertical or whatever. You could use other instruments such as a theodolite, a protractor, a compass, setting circles, an astrolabe, anything like that. This is just one example. It's an example I had in my own living room, so I took a photo of it. Virtually all the other photos come off the internet, but that's one of my own. A calculator. You're going to need a calculator to do the calculations when you take the measurements, and in particular you're going to need the trig functions quite probably in terms of calculating angles, sines, cosines for distances once you've measured angles and so on. And that is is largely it, but we might need a small coin as well.
An electric meter.
Much electricity for
I think I was about 12 when it was Bob through. Yeah.
We shall find out the use of a small coin in due course.
That was a brilliant question, Chris. I bet you didn't expect that one.
So methods, okay, so we decided we need a tape measure or a ruler, and we can directly measure things. If I want to measure the size of this table, I could take a tape measure and actually measure it. It's a method of doing something with a tape measure. Curious thing, this morning, I was just going through these slides, just checking them before putting them onto my memory stick or onto my daughter's laptop to bring here. I thought, this is rather odd. The 64 is in red and the others aren't. I thought, I'm sure on my tape measure, it's all the 12 inches that are in red. And I got my tape measure out, and sure enough, no, it's 16, 32, 48, 64, they're in red. I thought, how bizarre. I wonder why that is. Does anybody know? If you think about who's most likely to use a tape measure in general use?
Taylor.
Joiners.
Joiners, close, yeah, builders, workmen and so on. And when they worked in Imperial, whenever they're building rafters in ceilings, roofs and everything, the distance between the centres of the rafters is 16 inches. So they're always marking 16-inch increments on tape measures. I thought that was rather good, actually. Yeah. And it was just coincidental that I'm having an extension built at home at the moment, just about finished. And one of the builders was still there this morning, so I ran out and tipped and said, do you like these in red? He says, of course I do.
So he told you?
He told me, yes. Although I said I've had no idea.
So, measuring the universe, is it marked off in...
Astronomical.
Better than John, didn't know that.
Or parsecs. Yeah.
Okay, so other methods that we might use are trigonometry using triangles. So if we want to measure the height of a tree, we could climb up the tree, get a piece of string, hang a plumb bob down, a bit dangerous, a bit inconvenient and so on. Alternatively, we could measure the distance from the tree to where we are, and then we could measure the angle from where we are to the top of the tree, and given the angle and the distance there, we can then use the sines, cosines and tangents, or Pythagoras' theorem, or whatever.
So that was what maths was for?
That's what maths was for, yes.
No.
Measuring trees for that and to climb them. I won't be able to do
So,
it now.
so you could use the sine rule, the cosine rule, there's 18 different methods. There's more than one way to skin a cat. Right? So, yes, we can measure things without physically measuring them, just by doing angles. And that becomes, it's probably about the most fundamental method that we'd use in measuring anything big.
When did you first do that, Chris? Because I was 10 at primary school at Button Lane.
I can't remember when I first did that. I do remember when my daughter was about 12. She was with me. And, I mean, as parents, I'm sure you've never heard your kids say, Dad, I'm bored, on a summer's afternoon. And we were sat out on the patio, and we had the big tree in the garden. So I used the sextant that I showed you in the previous slide, and we had a table that was just over a metre long. So we didn't even have to measure this distance, because we took two sightings 1 metre apart on the table to measure D, and then did the vertical thing to measure the height. So just by using 1 metre rule on a table, we could measure the height of the tree. And I thought that was...
So you climbed it and measured it just to check you were right?
You're just showing us up as terrible parents, because I've never done that with my child. God, another black mark in the bad parent book. I baked cakes when it was board day.
Very likely, yes.
And you're the child protection officer.
Wasn't safe climbing trees.
Settle down, children. Right. Another thing is parallax. This is very much like trigonometry, triangles or whatever, but it's really done against the background, but it's essentially the same principle. So two people a known distance apart can view one object and can measure the angle and the amount of displacement you seem to get at a given distance, and that way you can work out the distance to other things. And it's very much like the experiment everybody's done 100 times when you hold your thumb out and cover some object with when viewing through one eye, then close that eye and open the other one, and it shifts. And if you know the length of your arm, you can work out the distance to the thing, and so on. You know. So it all works out. It's all done with trigonometry and so on. Right then, that's the tree, in fact, it's at the bottom of my garden. Now, I would ask you, how big is that tree? Can anybody tell me?
It's about 50, 60 foot.
You can't tell, that's a problem. You
can't,
don't know
there's
just
a
how
house
far
in
away or whatever.
There's a house in the back.
Yes, but that's even further away and so on. However, this tree no longer exists. I had it cut down about 3 years ago.
0 feet.
Trick question.
0 feet.
So now it's that
And
big.
it fed my burning stove for 2 winters. But when I wanted to get it cut down, I had to ring and get quotes for doing it. And one thing I was asked was, how tall is the tree? I said, I don't really know. I'll find out. So I went to my garage and I found a bit of 2x1 that I bought from B&Q and used, which was 8 foot long or 2.4 metres. Now if I ask again, how tall is that tree? Can anybody work it out?
Well, there's the pole at the bottom, isn't it?
Right, yeah. So this is 8 foot or 2.4 metres, right? And the point is, knowing that that's 8 foot, you can then, and it's a little bit over 40 feet-ish.
That's right.
Precisely, yeah, but it was a guess, that's the point. Now, you also said 60 feet as well, and the point is, you don't need to measure any angles, you just do it by comparing a known value against other things, right? So if you know the size of one thing in the field, you can often work out the size of other things. And this can prove useful in measuring other things in the universe, whether it be distance or height, width or whatever. The point you compare one thing with another of known value, and it gives you the unknown value that you're trying to work out. Another possibility is that we can use timing. And I'd say consider this in a more general sense. I mean, if somebody runs 100 metres in 10 seconds, you can quite easily work out their average speed, right? Because speed equals distance divided by time. But you can rearrange that so that distance equals speed times time and so on. And if we're looking at something in the universe, in the heavens or whatever, and we might know its speed, or we might know its distance, we might know, and we can time it moving somewhere, so we can work out the unknown value if we know any of the other two, right? So this is something we can often do. And an obvious example is using a laser beam to measure something. You know the speed of light at which the laser travels, you know the time it takes to do the return trip, and you can work out the distance because you've done it with a clock and so on, and no ruler required.
That's how we do it with the moon.
Precisely. That's coming up. And another one is redshift, but this is getting a bit more technical. I will say more about this later because we need to discuss a bit later, but we'll leave it until then. Okay, so we now want to actually measure the universe. We've got to start small and work out. We're on this Earth, we need to know how big is the Earth. As I said in the first slide, Eratosthenes was the first person to do a documented effort of measuring the size of the Earth. And he noticed that on a particular day, at noon, there was a well in Syene, or Aswan, as it's now known, on the Nile. And the sun shone straight down to the bottom of the well. It was directly overhead. Whereas in Alexandria, it wasn't. It didn't shine straight down the well. And he could measure the angle of the sun's rays on the well from how much it was displaced. And he knew the distance between Syene and Alexandria. So from that, you've got your well here, Alexandria's here, and it creates an angle there, which is the same as this angle here. So if this was, say, I don't know, 69 miles, and this was 1 degree, then that would give you a total circumference of the Earth of whatever it happens to be. It's one of those figures that I think Richard carries around in his head.
New radius.
The answer he got was 5,000 cubits.
No, it was 250,000 stadia.
Okay. Sorry.
Yeah.
No, that's right.
Yes, he worked out as 250,000 stadia, right? Which is fine, possibly, or not. Unfortunately, there was no standard definition of a stadia, and nobody knows which definition he was using, so nobody can really tell just how accurate he was. But in a sense, it's actually irrelevant. The point is, he measured the Earth's circumference in a unit that was convenient for him, but he then went on to calculate the distance to the Moon and the Sun. And if we assume that he got it spot on with the Earth at 250,000, so the stadia was whatever it needed to be exactly right, his distance to the Moon was effective, it would have worked out about 125,000 kilometres instead of 400,000, so it was a bit low for the Moon. Yet he worked out for the Sun that it was 804 million stadia, which would work out at I've forgotten, about 129 million kilometres, which is a tad low. It should be 150 million kilometres. So it's only about 15% low on the Sun, but it was about 70% low on the Moon. So I mean, good efforts, but given the technology and the tools that you had to work with, I mean, I suspect a stadium was a number of paces which could vary from person to person. So the actual value he was going to get was always going to be a bit iffy. But as a technique, it was very good. Incidentally, if ever you are thinking about the circumference of the Earth, the best way to remember it is in kilometres, because it's 40,000 kilometres, and almost by definition, because the metre was originally defined by the French as 1/10,000,000th of the distance between the North Pole and the equator through Paris, which is 10,000 kilometres. So the whole circumference would then be 40,000 kilometres. But they've since redefined the metre as some wavelength of
It's in terms of light now. Just the speed of light defined as.
Right, yes. And so, yeah, but I think it's now about 40,003 kilometres or something around the pole circumference. But if you want a rough and ready value, that is definitely the best way to remember the circumference of the Earth, doing kilometres.
Are you a racist?
We'll get a load of thumbs down from the French viewers.
Similar method here, but a little bit more astronomical, would be to use Polaris. Polaris is always a set distance above the horizon, depending on your latitude. And if you can do a measurement from two different places of the height of Polaris, then you can work out the difference in latitude between the two, and hence you can calculate the circumference of the Earth. This is probably easier than using the sun method, in as much as using the sun you've got to do it at the same time in two places, or you've got to calculate the difference in day times between the days that you do. Whereas here, the same person can do it on adjacent or different days. If you want to be super accurate, you do it 3 minutes and 56 seconds. Is it earlier or later the next day? I can never remember which. It must be later, I think, isn't it? Yeah. This idea was days.
Just so short here.
Yeah. So yes, if you travelled 100 miles for the next day and took the measurement 3 minutes and 56 seconds later.
Was it still clear?
Well, yeah. Or you wait for the next night and do it 3 minutes 56 seconds later again. Then yes, it'd be super accurate. But I mean, Polaris only moves by half a degree over 12 hours anyway, so it's never going to be a great deal of difference if you're a few minutes out. So that's probably a slightly easier method, and certainly more relevant to our pastime anyway, I would say.
Presumably when the Greeks were doing it, it wouldn't have been the pole star then. So,
well, this is true, yes, because the pole star
harder task.
yes, it does change over time. It's every 24,000 years the pole star effectively does a pole does a loop in the sky every 24,000 years. So 2,000 years ago, it would have been quite a way, 1/12 of the way around the circle. Yes.
Nature's always mucking things up.
During a human lifetime, it doesn't change enough to worry about, but over 2,000 years, it moves a long way, yes. So yes, you're quite right, the Greek couldn't be, well, they might have been used this method, but it'd been in a different style that they'd been using. Yes, it wouldn't be Polaris. Okay, so we've now measured the Earth, and now we want to measure the distance to the Moon. How might we do this? Well, one method that is quite obvious, I suppose, is to use a parallax or triangulation method, where from two different places on Earth, you sight the Moon and measure the difference in angle, and if you know this distance and so on, you can calculate the distance to the Moon. It has a few drawbacks, in as much as, you've got to be a long way apart to make your baseline sufficient to be able to get a meaningful angle. Secondly, third, fourth, you've got to make sure that this line is along the line of motion of the Moon and not across the line of motion if you're sighting against background stars and so on. You've got to do things simultaneously, and this gives rise to other problems. A young lad in Norway or Sweden, I'm not too sure, his name was Christoph Skok or something like that. He emailed out this to the astronomical community a year or more ago now, saying he was doing a school project and he wanted to do precisely this. He wanted to photograph the Moon from Norway, where he lived, and get somebody else to do it a long way away, to do it with him. I couldn't help him with that, but I did give him another method of doing it and put him in touch with a man called Colin Henshaw, who did help him. Last time I spoke to Colin about 6 months ago, and they were still trying to do it because they had to coordinate their times exactly. They had to get a night when it was clear, both in Norway and in Saudi Arabia or wherever it is that Colin is now.
Right.
You know.
So basically like in Norway.
Possibly. Well, you could get dust storms in Saudi Arabia, though, you know. And therein lies its own problem, getting good weather conditions in two very disparate parts of the world. And then you possibly have to take into account the curvature of the Earth as well, and your angles and so on. It becomes quite a complex and difficult task. Not impossible, but you've got to take all these things into account, and it does make it quite difficult. So, what else could we do then? This is a method that we did here in the Society about 20 years ago. I remember I proposed it as a project for the Society, and everyone said, oh, that's a good idea, and I went through the method and everything. And at the end of the meeting, a chap from the audience, whose name was Peter Ball, came up to me and says, I remember watching that on the Open University many years ago, and I said, I was watching exactly the same programme. So, what do we do here? Right, well, this basically relies on using eclipses, right? Now, during a solar eclipse, that's when the Moon moves between the Earth and the Sun. Here, so we've got the Sun out here, a long way away, shining light, and it casts a shadow that goes from one lunar diameter, which I've called D here, down to 0 effectively. I know sometimes it's a few miles across the shadow, sometimes it doesn't quite reach the Earth depending on how far away the Moon is at that given time, because its orbit is elliptical. But effectively, it goes from one lunar diameter to nothing over one lunar distance, which is very, very convenient, really. Now, it does rely on the Sun being much further away than the Moon, but fortunately we know that that is true, whether we've measured it or not, and I can prove that to you in a few slides, so I will come back. It is an assumption, but it's one that we can rely on. Now then, when it comes to a lunar eclipse, this is when the Moon goes into the shadow of the Earth, so the Earth is between the Sun and the Moon. And during that eclipse, the Earth's shadow tapers down, and we can assume, because the Sun's much further away and much bigger, it'll taper down by exactly the same amount as that. So it'll taper down by 1 lunar distance. So the Earth's shadow here will be the Earth's diameter minus the Moon's diameter, right? We know the Earth's diameter, but we don't know the Moon's diameter, so that we need to work out. And for this we need a small coin, not for the electric meter. So what we need to do is get a small coin, hold it up and eclipse the Moon exactly with the coin. But first of all we need to measure the coin. Now the best way of doing that, you can get your ruler out and measure your coin. If you can measure to an accuracy of 1 millimetre, you get a value, I don't know, say 12 millimetres, whatever it is. Better still, put 10 of them in a line, measure those, divide by 10, and you've got it accurate to a tenth of a millimetre then. Do it with more if you want to, but you know, 10's sufficient.
It's inexpensive.
It is, yes. Yes, Yorkshiremen would do it with 5, yeah. Now, a word of warning, when we tried this, way back when, 20 years ago now, I remember Derek and Chris were the first to try this bit, and Derek rang me up on the phone and said, "We've got a problem, Chris. We can't hold the 5p far enough away." Now, I thought, you could be joking, the 5p is fine, but you cannot hold it far enough away to eclipse the Moon, right? It's too big. This really is just how small the Moon is in the sky. You might think it's quite a bit bigger, but you know, a 5p is just too big. So what we have to do, we've got a long piece of wood, a piece of blue tack and stuck the 5p on, and then used a sighting angle and pointed at them. You just move the sighter back and forward until you got exactly the point where the 5p eclipses, and you can then put a scale on the edge so it could measure it. And then each of us did that 3 or 4 times, took an average for each, and you know, we got our values. Right? So once you know this distance and you know this size, you can calculate that angle. So you know the angle that the Moon subtends at 1 lunar distance. Next, we do the same procedure but during the lunar eclipse, right? But you basically now want to measure the Earth's shadow. But you can't do that while the Moon's in full shadow, because you can't tell where the edge of the shadow is. You've got to do it at one of these points just as the Moon's going into or coming out of shadow. And you can see the curve of the Earth on the Moon, and you line up your 5p piece with that. And then you can find the angle subtended by the Earth, or by the Earth's shadow, at 1 lunar distance. What that effectively gives us is 2 triangles, one for the Moon and one for the Earth. Add these together, the d's cancel out, and we know what big D is, that's the diameter of the Earth. So we know this distance here, and we know this angle here, we can just add these 2 together. Now I know that purists are going to say, you can't just add angles together. In this small geek, I know you meant to use something like sin x cos y plus cos x sin y, but for small angles, it really is, it's sufficient to just add them together. I think I've got the formula right. It's 35 years since I did my maths A level, you know.
Are you impressing me? You're impressing me.
So, yeah, we know the angle here, and we know this distance here. And what that sort of simplifies down to are a couple of right-angled triangles, or you could use the sine rule or the cosine rule, or you can, as I said, do this and use sines, cosines or tangents or whatever twice and double it. But the point is, that then gives you this distance here, the distance to the Moon we've been after. I think that's quite elegant personally, but you know. As I said, we tried that here about 20 years ago, and we've got a value of about 179,000 miles, which is a bit on the low side. Possibly better than Eratosthenes, and the actual value is about 250,000 miles, so we're low by, you know, sort of, I don't know, 30% or something like that. But you know, if we'd taken a bit more care, we could have firmed it up a bit better than that.
Should have used a 2 quid coin then instead of a 5p.
You'd need a very long piece of wood then to hold it on, I'll tell you. A more modern method, already been alluded to at this point, bounce a laser beam off the Moon and time it. This is what is done every day, apparently, from an observatory somewhere in America. They shine a laser beam at the Moon and time it. It's this reflective array that was left there by the Apollo astronauts. And it has this curious property. It's made up of these right-angled mirrors. and whatever direction the light comes in, it always goes out at the same angle. So the light always goes back whence it came, not reflected off and so on. So it makes it very useful. You want to hit it vaguely, and the light will come straight back to you.
Do you remember when we used to use cycle
Bicycle
reflectors?
Yeah, I remember that.
Because they are corner reflectors,
Yes.
which is why you can see them from any angle if you shine a light at them.
Yeah. Yes.
They are
Same
total
thing, yeah.
internal reflection.
Yeah.
Someone gave a talk, didn't they?
They're clever, but cheap.
Oh yes, absolutely. Yeah. That's a very simple idea, and it just allows this to happen.
And it's 10 o'clock.
Well, I'll talk a bit faster. Okay, so now we found out the distance to the moon. Want to know the size of the solar system? Thought we can use Kepler's third law of motion, which basically states that the square of the period is proportional to the cube of the distance. And by taking the right units, the k drops out. So 1 year takes the Earth 1 year to go around the Sun, and it's at 1 astronomical unit. Jupiter, for instance, we know takes about 11.8 years. So I said we might need a watch or something to calculate. You'd need a calendar to calculate the orbit of Jupiter in terms of how long ago. 11.8 squared is 139 or something like that. Take the cube root of that, and it's about 5.2. So Jupiter, is then 5.2 times further away from the Sun than the Earth. So, I mean, all periods of the planets have been known for a long time, so it's quite convenient in that respect. But all distances are now relative to the distance of the Earth from the Sun, which we call the astronomical unit. And we now just need to work out one absolute distance. This is the distance to the Sun we need to calculate. Now, I said before that we knew that the Sun was much further away than the Moon. This is why we know. This is what they tried in ancient Greek times. From the Earth, you view the Moon at first quarter or third quarter, when the terminator is exactly level. Then you've got a right angle between the Moon and the Sun, and you calculate and you measure this angle to the Sun, and from that you can calculate the distance to the Sun. It has a big flaw in it. It's logically sound, but this angle is about 89.8 degrees or something like that. And I think Eratosthenes worked this angle out as being 1/7 of 1 degree. But that told him that, even with his inaccuracies, that this distance was about 400 times this distance. So, even if he was a bit out, he knew that the Sun was much further away than the Moon. It didn't matter how far away it was much further away. And that's what we needed to rely on for our earlier method of measuring the distance to the Moon, which we can now say was true. Fortunately, we have another method, and this one I alluded to earlier, and that's during a transit of Venus. These are events when Venus appears to cross the Sun's disk. They happen in pairs, 8 years apart, and then it's another 150 odd years before the next pair, and so on. We've just had the last one, didn't we, within 2012?
About 21, 25 or something.
Yeah, it's about 158 years or something before the next one.
We videoed it in 2004 and worked out the distance. You could do it on the internet. Do you remember the figure we got?
I can't remember, I wasn't there because I was in Japan at the time.
We got 92.4.
Oh, pretty good. 93 is the accepted value, but depends on the time of year then as well, because, so it might be spot on. But yes, using this method, using triangulation from 2 points on Earth, and timing Venus going across the
It was in June, so we're further away there.
Yes, we are, yes. So, it was James Cook. James Cook on the HMS Endeavour. He went with astronomer Charles Green, who did the actual measurements, but Cook seems to get all the glory for it.
The angle's very small.
Oh yes, the angle's very small indeed. Yes, you're talking about much less than 1 degree. Yes. Right then. Now we want to measure to the nearest stars. What this is showing is a top-down view. This is the Earth going around the Sun. We know that this distance is 300 million kilometres, 2 astronomical units, when the Earth is 6 months round its orbit. So with a baseline of 300 million kilometres, we should be able to get quite a bit of parallax on the nearest stars. Not a bit of it. The stars are so far away. The angle that you get on even the nearest stars is much less than 1 arc second. That's 1/3600th of a degree.
Yeah.
Despite that, modern telescopes and instruments can measure up to 40 parsecs, or a parsec is 3.2 light years. It's about 130 light years.
Chris, it's hurting my head now.
I'm sorry, I'm going to go past it. There's people want to go to the pub.
I was going to say,
But one method of seeing it is taking photographs of the two and then superimposing them. Now, when I got this off the internet, there was some text saying that if you use the autostereogram visual on that, the things merge. I tried doing this and it did it out on my screen. I don't know if you could do it here. It all depends on whether you've got the right distance and so on. But the two pictures merge and the central stars stand out as different because it's moved a little bit. But it's quite an interesting effect seeing it on your computer screen, and it almost goes to 3D. It's very weird. Yes. But
Are you suggesting that we go cross-eyed to look at the two lower
Yeah, I've got it.
pictures so
Yes.
they superimpose?
I've got it.
yeah, you've got it. Yeah.
Yeah,
Yeah. I said it really is quite an impressive thing.
really good.
Yeah. But yeah, because I didn't think I'd be able to do it on computer. There's too much else cluttering it up. But no, it still did it. I was really quite impressed. But I think we'll move on anyway because we're getting a bit.
Yeah.
Right. Going further distances, one method that we use is looking at open clusters. This is showing an open cluster as it's moving through space at a given distance, and viewed from a sideways on, it appears to be moving into a vanishing point, and you can measure this distance theta then by using the recessional velocity, which can be calculated from using redshift, which we'll talk very briefly about in a minute. You can then calculate the distance to the open cluster. Talked about comparing things before. Comparing brightness of stars is a very effective way of calculating distances, especially with certain types of stars. And these are our Lyra stars. They're called that purely because they're named after the first star that was found to be of this type in Lyra. And basically, they're stars that are about 1.5 times the size of the Sun. They've burnt up all their hydrogen, they're now burning helium into carbon, and because of this, they're fluctuating in size and brightness periodically. But strangely enough, this period is directly proportional to their actual brightness. So the longer the period of dimming and the brighter or dimmer the stars, I don't know which way around it is. Unfortunately, RR Lyra stars are intrinsically quite faint, so they're only good for a few thousand light years for calibrating. But it's another method that we have for getting out there to the stars. More commonly, as Cepheid variables, they're much bigger, between 4 and 20 times the mass of the Sun, up to 100,000 times brighter. And they're used as standard candles. So basically, something that's bright looks a lot brighter when it's nearer to us, but the same candle looks a lot dimmer when further away. And Cepheids, like RR Lyras, pulsate because they're at the end of their life, and the inward pressure from gravity is catching up with the outward force of the generated by the nuclear fusion. And the period of it brightening and dimming is again directly proportional to its actual brightness. And we'll just say a little bit more about that in a couple of slides' time. There are a few other methods as well, which I won't elucidate on, but things like proper motion, secular parallax, statistical parallax, kinematic distance, Barlow-Vesselink method. There's hundreds of them for different types of stars, or they're useful in different circumstances that they can use to calibrate the distance to various stars. So I want to say briefly about this young lady, Henrietta Swan-Leavitt. She was born in 1864 and died in 1921, I think it was. She worked at the Harvard College Observatory as an unpaid worker because she was a woman of her own means anyway. And she worked as a computer. That's not a strange thing. In those days, a computer was somebody who did calculations. It wasn't a physical device that does the things for us. And she kept all variable stars and so on. And she worked with these. And she had a method of taking photographic plates and making a negative of one, positive of another, overlaying them, and the two would cancel each other out, except for those variable stars. Really quite a nifty method, I thought. In her life, she discovered 1,200 variable stars, which at the time was half of all the variable stars known in the sky. But one thing that she did, she worked with Cepheids a lot, and she found a lot of Cepheid variables in the Magellanic Clouds. And she plotted them, and she could tell that their periodicity directly matched their brightness. But then she made a great leap of faith and said, but because they're in this little cluster, they must essentially be the same distance from Earth. So that told us that the periodicity directly matched the actual brightness of the star, which allowed us to use them as standard candles. And these stars are so bright they can be seen in external galaxies. So we could actually tell the distance to galaxies beyond our own. So our first method of measuring distances to galaxies is these Cepheid variables, thanks to Henrietta Swan-Leavitt. But the man that did most with galaxies was Edwin Hubble, as we already know. And he worked at the Mount Wilson Observatory in California. And he used Cepheid variables to calculate the distance to many galaxies. But in doing this, he also took spectroscopic details of the light of these galaxies. And although redshift wasn't down to him, that was first discovered in about 1845, he noticed that the galaxies exhibited what's known as a redshift. Now, each element absorbs different frequencies of light and causes these black bands in the spectrum of light, and that is unique to each element. Now, in something coming from a stationary light source, you get something like this. But when it's moving away from you, these lines get shifted down towards the red end, hence the name redshift. And he noticed that the further away a galaxy was, as measured by a Cepheid variable, the greater the redshift of that galaxy. Now, the redshift is a function of the speed of the galaxy as well. So he also worked out that the further away a galaxy was, the faster it was moving, which seemed a very strange result, but it's something that we now live with and understand. But he was the first person to work this out. But this gave us a method of measuring galaxies much further away than any Cepheid variable would allow us to. And now we have redshifts up to, is it something like 4 or something like that? You know, there's some huge factor, which is getting us well out into several billions of light years away, which give us the confidence to know that we do have quite a good fix on the size of the universe. So, in conclusion, you'll all be glad to hear, we've looked at the tools that are at our disposal for measuring the universe. We've looked at the methods that are available to measure the different scales of distance. And when we can use more than one measure on any given thing, that allows us to verify that the two agree, which increase our confidence that the values that we do have for the universe are in fact correct. And one final point, if at this point you feel that you're no wiser than you were an hour ago, at least you can be comforted by the fact that you are now better informed. Thank you very much.
So, Chris, one of the things you missed out there is that they use quite a lot is type 1A supernovae.
Yes.
Yes.
There's only so many you can do that.
Yes. The other one I was going to say is I did a talk, was it last year or the year before, about Gaia, the new European Space Agency program.
Oh yes, yes, I remember.
And you can actually they're trying to measure direct parallaxes up to about 5-6 micro arc seconds, so
Right, yes, so
millions of arc seconds.
yes.
Yeah. But that I think gets launched in December.
Oh, that's
So
going to
it's
get launched.
soon. Yeah.
Thank you very much.
Chris,
Don't like
and,
the use of differential
I
equations.
think
Oh,
it's
it's
fine.
fine.
Let's see.
Excellent, Chris.
Oh,
physics and
just so
astronomy
you
as
know
well.
about
I passed an email round earlier, folks, about Tony. And I know many of you have been friends with Tony for years and may have your own arrangements. But I didn't know if our friends here would like to maybe put towards a collection